Good morning, students. Today we'll see how to draw frequency response of common emitter configuration amplifier. For that purpose, I have chosen some readings for corresponding input frequency and the input voltage for the signal was 50 millivolt. The frequency of input signal is change from 50 Hertz to the 5 megahertz. For calculation purpose, I have put two way the presentation. One is written in terms of Hertz as a labeled, and this is here in terms of value. When we calculate its output voltage comes in this range. It varies from about 9 millivolts to maximum to 2.33 volts, and again come back to 0.1 volt. So if we taken a ratio of input voltage to the output voltage, we get a gain in terms of I'm going to say it's a ratio of output voltage to the input voltage, that is AV. And if we calculate it in terms of decibel gain, it will come to this way. For 50 Hertz it's 5 dB, for let's say 1000 Hertz it is 32 dB, and so on. For the whole range of 50 Hertz to 5 megahertz, I have calculated the AV, and from that on Excel we have formulated it. And if you observe this chart, the scale chosen here, this is scale. If we take a formatting of it, we have chosen is a logarithmic scale, right? So for this logarithmic scale, for all these values of from 50 Hertz to 500 megahertz, by putting all those values we can draw the graph on the Excel format. Now same thing I will demonstrate you on the semi-log paper after this small video. But for understanding purpose, on this axis we have gain, which this axis is a linear axis, and where we are pointing out 5 dB, 10 dB, 15 dB, means each division is of 5 dB, and corresponding to the frequency values on this axis, frequency was in Hertz, 50 Hertz to 5 megahertz. We have plotted the points over the graph for corresponding frequencies, and then we can able to see the output of our frequency or you can say frequency response of a common emitter configuration amplifier in this fashion. After that, we have just calculated 70.7% of the maximum value. Maximum decibel value was 33, and the 70.7% was coming about 23.33. So we have drawn one line indicating 2 points. One is cutting this point about 23.33, and this is also 23.33. If we take a projection of this, we will get a lower frequency somewhere here about 100 Hertz, and somewhere about here about 2 megahertz. So broadly we can say our bandwidth of our amplifier is about 100 Hertz to 2 megahertz. So we can say our amplifier can efficiently work in the range from 100 Hertz to 2 megahertz. After this, I will show you how to draw physically on the graph paper. Thank you, students. Okay, just I'm briefing you about semi-log paper. This semi-log paper is having this logarithmic scale, where you can see, if I go and focus you on this, if you're able to see it very clearly, it is divided into 10 lines. One is there. I've started it at 10, so this will become 20. This will become 30. Then you can see major line 40, then major line 50, 60, 70, 80, 90 and 100. So it's actually compressing away. So say if you take another look at 100 to 1 kilohertz, it will be similar way: 100, 200 hertz, 300, 400, 500, 600 and so on up to 1 kilohertz. Same way you can go ahead, 1 kilohertz, then you will have 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, 6 kilohertz, 7, 8, 9 and 10 kilohertz. So this way you can have the scale on a semi-log paper. Good afternoon students. For frequency response of common emitter configuration, we'll take this reading. We'll take from 100 Hz to about 2 megahertz reading, 5 megahertz reading, where we have on one axis frequency and on another axis we will have gain in terms of decibels. Was assuming that we were applied input voltage of 50 millivolt. So for that purpose we have semi-log graph paper. This scale is a logarithmic scale, so it starts in a decade. So I have mentioned here frequency on this axis, starting from frequency 100 Hz, multiple of 10 times to it, that is 1 decade, is 1000 Hz, which is 1 kilohertz, then 10 kilohertz, 100 kilohertz, 10 times of that will be 1 megahertz, and 10 times of that will be 10 megahertz. On this vertical axis we have gain. Gain is mentioned in linear way, 5 dB to 40 dB. So looking to our readings, first reading was at 100 dB. So at 100 dB the gain was 5. So I am just pointing out that point 5 and marking the circle to it. Second point was at 200 Hertz, that is 22. So this will be 200 Hertz. So at 200 Hertz 22 dB will be this point. So I'll mark that point. Then 500 dB, 500 Hertz 31 dB. So I'll mark at this line 31 dB. Right? This scale is subdivided into 5 lines. So each line can consider to be 1 dB. Then next point is at 1 kilohertz. This is 32 dB. So at 1 kilohertz I will have 32 dB point. Then at 5 kilohertz 33 dB. So 5 kilohertz will be this one, 5 kilohertz. At 5 kilohertz it is 33 dB. So I'll go and mark on 5 kilohertz this vertical line 33 dB. So I'll point here at 33 dB. Then 10 kilohertz, 50 kilohertz and 100 kilohertz are same value. So 10 kilohertz again 33 dB. Then 50 kilohertz, this is 10 kilohertz, 20, 30, 40, 50 kilohertz. At 50 kilohertz again I will have 0.33 dB. Then at 100 kilohertz also I will have 0.33 dB, because maximum gain is now I am observing is 33 dB. At 500 kilohertz, so this is 100 kilohertz, this will become 200 kilohertz, 300 kilohertz, 400 kilohertz and 500 kilohertz. At 500 kilohertz I have gain as 31 dB. So I'll point out that point here. I will locate that point on the graph. My semi-log graph pair is 31 dB. Then at 1 megahertz gain drops to 28 dB. So I'll go and point out the 28 dB point. And then at 2 megahertz it's 18 dB. So at this is 1 megahertz, so this will be 2 megahertz major line, and that will be 18 dB. So 18 dB I am pointing out here somewhere. And at 5 megahertz it is 6 dB. So this is 3 dB, 4 dB, 2 megahertz, 3 megahertz, 4 megahertz, 5 megahertz. At 5 megahertz I have out gain at 6 decibels. So 6 decibels will come somewhere at this point. So looking to this point, if you have French curve, you can draw using French curve, point joining this point, or you can draw freehand like this way. I'm joining those points, assuming that there will be sharp curve, and if you calculate or you draw it some way like this, you will able to draw frequency response. Okay, now if you take another maximum value you are going to get here. So if I assume 33 dB is a maximum value, if I calculate 70.7% of it, it comes about 23.33. So I will mark one simple dotted line on 23.33 or about 23. So I am going to get this dotted line at 23. So I got a dotted line. You can use a scale directly, and getting 2 points, one point at this point I can project it down somewhere coming here about 200 Hertz, that I am saying it is FL, lower frequency cutoff. And if I drop down this point or project this point here, it is about 1.4 megahertz, right? So broadly, if I taken a difference between these two, it is, this point is said to be FH, higher frequency cutoff. So the bandwidth can be calculated as FH minus FL. So FH is about 1.4 megahertz minus this 200 and about 200, and this is 240 hertz. So if you take a difference of it, it will be the bandwidth of the frequency response of common emitter configuration. So by this way you can draw your frequency response on semi-log paper. Thank you, students.